Welcome back to the Deep Dive, where we tear open the most intense research papers and reveal the surprising foundational insights that are reshaping artificial intelligence.
Today, we are diving deep into, well, probably the single biggest choke point facing large language models right now, the context length bottleneck.
Ah, yes.
We've been celebrating those massive context windows, hundreds of thousands of tokens, but the computational reality is just brutal. Processing these gargantuan sequences is quadratically expensive, it's slow, and frankly, often prohibitively costly.
That's the perfect setup for today, actually. We're discussing a paper released by the DeepSeek team titled DeepSeek OCR.
Right.
And the title is, quite honestly, a brilliant piece of misdirection. Because if you hear OCR optical character recognition, you immediately think, okay, scanning documents, standard stuff, right?
Exactly. But you'd be wrong. This paper holds a secret weapon.
Okay.
The breakthrough here has almost nothing to do with just improving simple character recognition, though. I mean, it does that pretty well, too. The actual revolutionary concept introduced and validated here is context optical compression, or COC.
Context optical compression. Okay, let's immediately try and define this paradigm shift.
Yeah.
It's the radical proposition that instead of feeding a massive document, maybe a, 50-page legal brief, into an LLM as this sequential string of costly text tokens.
Right.
You first convert the document into an image, like essentially a very high-resolution screenshot.
And here is the core thesis of the paper, stated pretty eloquently, I think. If a document contains, say, 1,000 characters, generating maybe 600 or 700 text tokens, how many visual tokens, the compressed representation of that image, do we actually need to retain full accuracy? The authors are basically betting that a picture is worth 1,000 words isn't just some old adage, but it's actually a computational truth.
A computational truth. I like that. So for you, the listener, we are going on a mission today to really understand that computational truth. We'll cover the economic motivation behind this intense need for compression, the VLM architecture that makes this whole visual trick possible, the ingenious sequential design of DeepSeek OCR that achieves these record compression levels.
And maybe most importantly, what this means for the future of AI agent memory and context management. That's where it gets really interesting.
Definitely.
So let's start with the economic reality that really drove this innovation. Why text tokenization just fails at scale.
Right. So every LLM starts with tokenization. You input a long string of text, and a tokenizer breaks it down into these small units, typically subwords. And if you have just a single academic paper, that could easily be, tens of thousands of tokens.
Oh, easily. And that sequence, once it's tokenized, becomes the input vector for the transformer architecture.
Right.
The issue, as we often discuss, lies in the self-attention mechanism. That's really the heart of the transformer. To understand the relationship between every single token in the sequence, the model has to calculate the interaction between every single pair of tokens.
And this is the infamous quadratic problem, isn't it?
Precisely. If your sequence length is $, the cost scales roughly as tool of 2.
Right.
So if you double the length of the document, you don't just double the processing time. You actually quadruple the processing time and the memory requirement for storing those huge attention matrices.
Okay, yeah.
And when documents extend to hundreds of thousands of tokens, the cost explosion just becomes catastrophic. It restricts the maximum effective context window, regardless of how much memory the GPU has, simply because the processing time is too long and the cost is way too high.
So the DeepSeek team looked at this fundamental scaling problem and basically said, okay, we need to cheat somehow. We need to find a way to make length of the sequence drastically, radically shorter before it ever touches the transformer's main attention layer.
And that is exactly where context optical compression, or COC, steps in as the surgical solution. The first radical step, as you mentioned, is converting the document into a visual format. Think of it like a PDF or maybe a high-resolution image file.
Okay, wait a minute, though. If we treat text as an image, doesn't that inherently introduce some risk, like ambiguity or noise that standard text tokens avoid?
That's a really good question.
I mean, text tokens are discrete. They're perfect representations. An image of text is continuous. It can have anti-aliasing, font issues, maybe just blurriness. How do they make sure that visual encoding doesn't actually degrade the underlying information fidelity?
Yeah, that's a crucial point, and it's exactly why the entire architecture is so carefully tuned. The key is in the vision encoder's ability to extract semantic features rather than just raw pixel data.
Oh, yeah.
The encoder's job isn't just to see the picture. It's trained specifically to see the structure of the characters and the layout of the text within that image.
I see. So the vision encoder isn't reading the text in the traditional OCR sense, like character by character.
Not exactly.
It's identifying dense structural information patches. Is that right?
That's a great way to put it. And then step 2 is the compression itself.
Right.
The vision encoder breaks the image into these patch tokens or visual tokens. And because vision models, specifically the vision transformer, the VIT architecture, are inherently really efficient at summarizing large areas of spatial data into a single rich feature vector, the number of resulting visual tokens is often far, far smaller than the original text tokens would have been.
Okay, so let's try and put this in perspective for you listening. If a document normally yields, say, 650 text tokens,
Yeah.
the authors wanted to prove they could represent that same information with maybe 60 or 70 visual tokens. Is that the kind of scale?
That's exactly the scale. We are talking about potentially reducing the sequence length $ by a factor of 10.
Wow.
And the beauty of that factor of 10 reduction is that it translates roughly to a 100-fold reduction in that quadratic computational cost.
Okay, that's huge.
This is the compression hypothesis, that visual features derived from these organized text-based images are redundant enough that they can be significantly downsampled without losing the core underlying linguistic information.
Right.
And the experimental results, as we'll see, show this wasn't just hypothetical, it was actually achievable.
Okay, so to really appreciate the sophistication of this compression, we probably need a bit of history, because this work sits right at the intersection of two fields that were, for a long time, totally separate paths.
Yeah.
Natural language processing and computer vision.
Yeah, absolutely. NLP's journey, involved moving from purely statistical methods like simple word counts, bag of words,
Right.
to the revolutionary idea of word embeddings, popularized by things like Word2Vec. Embeddings assign meaning and context to words by placing them in this high-dimensional vector space. And that intellectual leap really paved the way for the transformer architecture, which just excels at understanding sequential relationships in language.
And the transformer became the foundation for pretty much every major LLM we recognize today. GPT, BERT, Llama, all of them.
Yep.
It proved that simply scaling the data and the model size, using that self-attention mechanism, led to these profound improvements in linguistic understanding.
Meanwhile, computer vision followed a different track for a while. Initially, it relied heavily on manual feature engineering. Researchers would handcraft filters to detect things like edges, corners, basic shapes.
Right, I remember that.
Then that was largely replaced by convolutional neural networks, CNNs like ResNet, which learned those features automatically from data.
Okay.
And CNNs are highly effective, for sure, but they carry a strong inductive bias. Basically, they assume local spatial correlation pixels near each other matter most.
Right.
And that feature, that bias, often restrict their scalability and generalization when you compare them to these large, purely attention-based models like the transformer.
So then the vision community saw the power of the transformer scalability in NLP and thought, hey, maybe we can use that too.
Exactly. They adopted it pretty much wholesale, creating the vision transformer, or VIT.
Yeah.
And VIT was really the key convergence moment. It essentially discarded the strong local bias of CNNs. Instead, it broke the image into those small, fixed-size patches, typically $16 times 62-size pixels, linearized them, flattened them out, and treated that sequence of patches exactly like a sequence of text tokens in NLP.
So suddenly a large, complex image becomes just a very long sequence of these visual words.
Pretty much.
And once it's a sequence, the transformer can apply its powerful global attention mechanism to it, just like with text.
Exactly right. And this design choice was pivotal because it allowed vision models to benefit from the same kind of data scalability laws we were seeing in NLP. Performance just kept improving as the models were fed more and more image data, overcoming some of the saturation limitations often seen in earlier CNN architectures.
Okay, and this is what led directly to the development of vision language models, or VLMs, which are really the backbone of this DeepSeek OCR approach.
Yep. VLMs essentially unify these modalities. The standard recipe involves taking an already robust LLM, that's your linguistic backbone, kind of the brain,
And integrating a separate vision encoder to handle the images. The main goal is to make the image encoder output features that the LLM can immediately understand and process right alongside text inputs.
And the challenge, the really crucial step here, is alignment, right?
Absolutely.
The image features need to live in the same semantic space as the text features. Like if the LLM speaks English and the image encoder speaks visual, you need some kind of translator between them.
That translator is usually called the projection layer, or sometimes an adapter. It takes the high-dimensional output from the vision patches and transforms them, projects them into the LLM's text embedding space.
Okay.
Without that step, the LLM just receives visual gibberish it can't interpret. This alignment is really what separates a simple OCR tool from a true VLM that can actually reason about visual data in context.
And the gold standard for achieving this alignment, at least initially, was set by OpenAI's CLIP model, wasn't it?
CLIP, yeah. Released back in 2021, it trained separate text and image encoders using this technique called contrastive learning.
The idea was conceptually simple, but massive in scale. Feed the model millions upon millions of image-text pairs scraped from the internet.
Right.
And if the text caption matched the image, a brown cat sitting on a blue sofa, the encoders were trained to push their respective vector representations closer together in the embedding space.
Okay.
If they didn't match, the vectors were pushed further apart. And this approach created a highly effective shared embedding space, making it possible for VLMs to understand the relationship between what they see and what they read. Set the stage, really. #Tag3. The shortcomings of existing VLM architectures.
Okay, so we have CLIP, we have VIT, we have the basic VLM structure. But the moment researchers started applying these models to real-world documents, especially high-resolution documents full of dense text, they hit a wall pretty fast.
Yeah, they did. The standard VIT approach showed its limitations almost immediately.
What was the main issue?
The problem really goes back to that fixed patch size, usually $16 times 16:6 pixels. Imagine you train a model on a relatively small, say, 256 times 256 die image. That yields 256 patches, 256 tokens in the sequence.
Okay.
The model learns positional embeddings for a sequence of 256. It knows where token 1 is relative to token 256.
Right.
But now you feed it a much larger, say, $124 times 24 times image, like a full-page academic paper scanned at high res. You've just quadrupled the resolution in height and width.
Which means 16 times the patches.
Exactly. You've increased the patch count 16-fold, up to maybe 4,096 tokens.
Wow.
The model is suddenly seeing positions, sequence indices it has never encountered during training. It learned where token 100 sits relative to token 200, but now token 100 might be sitting next to token 2000 in this vastly longer sequence.
So the positional information it learned is suddenly irrelevant or just wrong?
Pretty much. It causes severe performance degradation. This resolution dependency forced researchers to seek these clever, sometimes convoluted workarounds to manage the sequence link explosion.
And this is the exact hurdle that DeepSeek OCR sought to overcome with their context optical compression idea.
Precisely. And the paper actually gives a brilliant critique of the three main, let's call them failure strategies used by other VLMs trying to handle high-resolution input.
Okay, let's break those down. What was the first failure mode they identified? The multiple encoder strategy.
Yeah. This was the approach taken by models like DeepSeek VL, the previous version, and also KBOR1. They used multiple specialized image encoders, all running in parallel. KBOR1, for instance, used 4 different pre-trained encoders like SAM, CLIP, maybe some specialized VITs, each potentially trained or fixed at different resolutions. Say, one handles $384, another $512, times 512 too, and so on.
That seems like a maybe logical approach. Cover all the resolution bases and just combine the outputs. What was the engineering flaw there?
Well, the major flaw is complexity and the resulting token bloat. If you run 4 separate encoders in parallel, you are generating 4 separate streams of vision tokens. Even if each individual stream is relatively short, when you concatenate them all together to feed the LLM, the final sequence length is still massive.
Right.
And maybe more importantly, you introduce significant deployment overhead. You need 4 separate inference streams running simultaneously, which greatly complicates the computational graph and increases latency and memory consumption dramatically. It's just an expensive, kind of inelegant solution to the sequence length problem.
Okay, so they basically traded the sequence length issue for parallel processing deployment headaches and still ended up with high token counts overall.
Got it. Yeah.
What about the second strategy, tiling?
Tiling. Yeah, this was seen in models like DeepSeek VL2. It attempts to solve the resolution issue by physically chopping the massive image into smaller, fixed-size tiles, maybe 448 times 448 pixels each. These tiles are then processed in parallel, often using the same encoder, and then the outputs are somehow stitched back together. Usually they add a small, low-resolution thumbnail of the whole image to provide some global context.
This sounds like a pretty common sense way to handle massive images like break it up and conquer. Where did it fail in the context of documents? Because documents are structured, right?
Exactly. Tiling fundamentally struggles with global layout information. For a document, understanding the hierarchy, like where the title is, where the footnotes are, which column comes before the next, is absolutely critical for comprehension.
Yeah.
When you process these tiles in isolation, they lose that crucial global spatial context. The thumbnail is supposed to provide it, but since the thumbnail has to be very small and highly compressed itself,
Right.
the global information is severely degraded. So you might perfectly recognize the words within tile A and within tile B, but the VLM struggles to confidently link those words structurally across the tile boundary if that relationship is only dimly perceived through the blurry context of the thumbnail.
Okay, so it maintains local fidelity, like the words in a small area,
Yeah.
but it loses the overall blueprint of the document.
That's a good way to put it. It loses the blueprint. And then there's the third strategy, which is maybe the most egregious failure mode,
Uh-oh.
the massive patch sequence approach. This was used by some models in the Quinn series or Google's NAT model.
I think we called this the brute force method earlier.
It is the very definition of brute force. Instead of trying to compress or tile cleverly, they simply take all the patches from a high-resolution image, all 4,096 tokens, for example, from our 1024 times 124 sequence, and feed that absolutely immense sequence directly into the transformer.
They just hope the hardware can handle it.
Pretty much. They just increase the sequence length dollars and hope the GPUs are big enough and fast enough.
And what's the inevitable catastrophic result of that?
Astronomical memory consumption and computational cost. I mean, think about it. If you have a sequence length of 4,000 tokens, you are calculating $4,000 times $4,000, which is $16.6 million attention scores per layer, per head.
Oh.
The intermediate activations, the tensors storing these calculations, become gargantuan, immediately consuming vast amounts of GPU memory. This limits your batch size, drastically raises inference costs, and ultimately means the model just cannot effectively scale to the truly long documents that sophisticated AI agents really need to process. And this is exactly what DeepSeek OCR recognized. We cannot keep forcing the sequence length to grow linearly, or worse, with the image resolution. The compression must happen at the input stage, intelligently.
Okay, so having laid out all of that necessary context and the failures of these existing methods, we can now really appreciate the elegance of the DeepSeek OCR solution. It seems they didn't just iterate, they created a kind of minimalist architecture centered entirely around this goal of efficient compression.
That's right. Their core architecture follows the VLM standard, a deep encoder for the image processing and a mixture of experts, or MoE large language model, as the decoder. But the fundamental design constraint driving everything was simplicity and minimalism. Minimize the visual token count while maximizing the decoding precision, the accuracy.
So how did they structure their deep encoder to achieve this really dramatic compression while avoiding the complexity of that parallel processing approach we talked about?
Yeah, the key innovation is the sequential encoder structure. They explicitly recognize that previous attempts to merge features from multiple sources, like the very paper, which one of the authors also worked on, often used parallel streams that just led to token bloat.
Right.
The sequential approach dictates that the output of the first stage acts as the refined input for the second compression stage. It's like a pipeline.
Okay, let's break down those two stages then. What's stage one doing?
Stage 1, local attention and feature extraction. This stage uses an improved VIT architecture that's actually derived from the SAM model, the segment anything model.
Ah, SAM. Okay, that's interesting. Why SAM?
The reason for choosing a SAM-based structure is pretty critical here. SAM is specifically designed to identify and segment objects and boundaries with extremely high fidelity, even complex ones. When you apply that kind of architecture to tutted images, this translates to superior recognition of individual character boundaries and the local text structure. It makes it highly effective at capturing the necessary fine-grained detail for reading.
So why not just use a standard VIT or maybe a swing transformer for this local detail part? They handle patches too.
Well, the SAM architecture and the specific derivatives they likely used typically employ non-overlapping window attention. This is similar to models like VRDET.
Okay.
This efficiently captures localized features without the computational overhead of running global attention across the whole image at this stage. SWIN uses shifted windows, which helps information flow but introduces its own complexity and slightly compromises computational parallelism compared to fixed, non-overlapping windows.
I see.
So the SAM-based structure gave them the local fidelity required for accurate character reading, but within a highly controlled, localized computational budget. Very efficient.
Okay, so we have the SAM-based encoder efficiently extracting the character details and the local text structure. Where does the actual compression happen then?
That comes in stage 2, global context and compression. The output feature map from that SAM-based local encoder is immediately fed sequentially into a CLIP-based module.
Ah, CLIP again.
Yes, and this module serves multiple crucial functions. It acts as the primary adapter or projection layer, aligning the visual features with the LLM's text space.
Right, the translator.
Exactly. And critically, it performs the aggressive downsampling. This is where the major compression occurs.
Okay, this is where we need the technical details. How does that downsampling mechanism work? The paper mentions something like a $16 times reduction in spatial dimensions. How can you shrink a dense feature map by 16 times without just blurring out all the crucial text details? That seems hard.
It is hard. The downsampling is integrated carefully into the vision encoder's structure itself. It likely uses specialized layers like perhaps strided convolutions or maybe non-uniform pooling applied hierarchically throughout the encoder stages. The key is that the vision encoder is trained during pre-training end-to-end to ensure that when it reduces the spatial resolution of the feature map, say going from $64 times $64 effective patches down to maybe $8 times 8 patches.
Yeah.
The resulting feature vectors in that smaller map are not just average colors or blurred pixels. They are trained to become highly semantic summaries of the text and structure they represent from the larger area.
So it's like intelligent pooling.
Yeah.
Trained specifically to prioritize linguistic data structure over raw pixel-level accuracy.
That's a perfect way to describe it. Intelligent pooling. Let's use that $124 times $24 example again. A raw $16 times $16 6-patch size would give you 40 over 96 tokens.
Right.
The deep encoder, through its sequential structure and these trained downsampling layers, reduces this massive potential patch sequence down to a fixed, manageable size of just 512 vision tokens.
512. Okay, that's a huge reduction from over 4,000.
Exactly. It's a controlled, almost surgical compression that directly feeds the LLM.
And the LLM, the decoder part, benefits from this immediately because it only has to pay that quadratic attention cost on the vastly reduced sequence length of 512 tokens instead of 4096.
Precisely, which is also why the decoder itself is designed for efficiency. They use a mixture of experts or MOE structure.
Right, MOE.
This means while the model technically has a large parameter count, I think it's 3 billion parameters in total, only a small, sparse fraction of those parameters, about 570 million, is actually activated for any given inference step.
Okay.
So you have a low token count input being processed by a sparse, efficient decoder. That combination equals maximum throughput and lower cost.
And we talked earlier about that infamous resolution dependency problem with VITs.
Yeah.
How did DeepSeek OCR handle that with this adaptive compression idea? They introduced those 6 different modes, right?
Yes, the 6 modes, they call them tiny, small, base, large, Gauda, and Gauda master, are the practical realization of dynamic compression. The authors recognize that the required fidelity, or sort of the amount of compression you can safely apply, changes based on the input document itself.
Right, like a novel written in a large font, all spaced out, is far less information dense than a 2-column academic paper filled with tiny subscripts and complex formulas.
Precisely. So the modes are tied to specific input resolutions, like $512 times 512 Tufertini up to $1,280 times $1,280 for Gauda master. And crucially, they target fixed output token budgets.
Ah, okay.
So for a simple low-density document, you might use the tiny mode, which outputs only 64 vision tokens, very compressed.
Mm-hmm.
For a high-density complex document, you'd probably use the Gauda master mode. This mode intelligently combines maybe dynamic resolution scaling and potentially even minimal tiling internally, ensuring enough visual tokens are extracted to maintain the fidelity needed for that dense information, but still keeping the output within a predefined manageable token budget, like maybe 512 tokens.
I see. So the approach makes the compression adaptive. It's efficient when it can be, but it ramps up the detail, the token count, when it absolutely must be accurate.
Exactly. It's not one-size-fits-all compression.
And the training pipeline they described confirms this complexity too, right?
Yeah.
They didn't just throw everything together and hit train.
No, it's a pretty classic staged VLM training pipeline, which really reflects their focus on getting that alignment perfect. Stage 1 is pure alignment. You freeze the massive LLM backbone and you freeze the complex image encoder weights. You only train the connecting tissue, that CLIP-based projection layer, the adapter.
Okay.
This ensures the visual features are perfectly mapped into the text embedding space before anything else starts to shift around.
Right. Get the translation right first.
Exactly. Then, in subsequent stages, they progressively unfreeze certain components, maybe parts of the encoder, maybe some layers of the LLM, and fine-tune the full system together to optimize the end-to-end performance on actual document understanding tasks. It's a very careful, layered approach to marry these highly specialized models effectively. #tag 5. Results and broader implications. The so what moment.
Okay, let's get to the validation then. Did this elegant sequential compression architecture actually deliver on its promise?
Yeah.
Did they really manage to achieve something like 10x compression without turning the text into, complete gibberish?
Yeah. The quantitative data they present emphatically says yes. They ran tests on text documents that, when tokenized traditionally using standard methods, generated sequences between 600 and 700 text tokens long.
Okay, so that's our baseline, 600, 700 text tokens.
Right. When the same content was converted into an image and processed by their deep encoder using one of the low-resolution high-compression modes, it was compressed down to just 64 visual tokens.
64, down from 600, 700.
Yeah.
That's staggering. We're talking about an average compression ratio of over 10.5x.
Yeah.
To put that in perspective again for you, the listener,
Yeah.
that's like taking a full technical manual and reducing the amount of data the LLM actually has to process down to the size of maybe a single highly compressed paragraph heading.
It's a massive reduction. And here is the really shocking part. Even at that extreme compression level of 10.5x, the model retained a precision of 96.05% on the task of reconstructing the original text.
96% precision at over 10x compression.
Yep. And when they increased the token budget just slightly, using a mode that output 100 vision tokens instead of 64, the precision climbed even higher to 98.5%.
Wow.
The authors calculate that the 600, 700 tokens of text they tested is roughly equivalent to about 7 full pages of a standard document.
So basically, we can take 7 full pages of detailed text, effectively transform it into a sequence of just 100 tokens that the LLM can process, and lose almost nothing in the process.
Pretty much. That single data point, I think, really validates context optical compression as a viable, high-fidelity technique for fundamentally solving that quadratic bottleneck problem.
Okay. Now, what about the actual OCR task, the thing the paper's named after? How did it do there?
Right. Well, even the highly compressed modes, like the Gotham Master mode, performed comparably to, or in some cases slightly better than, other state-of-the-art specialized VLM OCR models, like one called DeepSeek OCR.
Okay.
The key difference is the efficiency. DeepSeek OCR achieved this high accuracy using a dramatically smaller sequence length, fewer vision tokens than those other models needed.
But we should probably reiterate the necessary caveat they identified too, right? About information density.
Oh, absolutely. If you use the really low resolution modes, like tiny or small, outputting only 64 or 100 tokens, on documents with extremely high information density, think of those academic papers with tiny fonts, packed columns, complex formulas.
Yeah.
The performance does degrade significantly. You can't compress that much detail that aggressively without loss.
So that reinforces the point that the compression isn't magic. It has to be adaptive.
Exactly. If you try to compress a high-fidelity input down to a very low-fidelity output budget, you will lose data. The compression mode has to match the information density of the source.
Makes sense.
But what's impressive is the capability of the higher fidelity modes, like Gotham Master, to handle complex qualitative features beyond just reading text. Things like decharting.
Decharting, what's that?
It means pulling specific numerical data points directly out of visual representations, like bar graphs or pie charts, within the document image.
Ah, okay. So not just reading the labels, but extracting the actual data values from the chart's visual structure.
Precisely. It shows the VLM isn't just reading characters in sequence, it's actually understanding the spatial data relationships within the image, which is immensely valuable for real-world document analysis.
Okay. That is impressive. So let's pivot now to the so what. Where does this extreme compression technique, the COC, have the most profound impact outside of just making document recognition faster or cheaper? This is where the paper's implications for AI agent memory come into play, right?
Yes. And this is perhaps the most exciting potential application, I think. LLMs and AI agents that need persistent memory agents that need to hold context over days, weeks, or even months of interaction, they suffer from this chronic memory loss problem. They constantly have to decide what to forget to make space for new information.
Right. And today, the standard method for managing that long-term context is basically summarization, isn't it?
Pretty much. You summarize old chunks of the conversation, and then you insert that summary back into the current context window when needed.
But the downside there is obvious. Summarization is inherently lossy. You lose specific details, nuances, quotes.
Exactly. You lose the fidelity. Context optical compression offers what could be a vastly superior archival memory system. Instead of summarizing the full conversation transcript text, the entire transcript could be rendered as an image or a series of images, and then compressed using this DeepSeek OCR method. This stores the context as a highly compressed visual sequence, a very low-token memory blob that potentially retains nearly full fidelity if the agent ever needs to recall the specifics.
Okay, let's try and put some hypothetical numbers on this cost-benefit trade-off, because that's what a sophisticated listener really cares about, right? Efficiency.
Yeah, good idea. Imagine, say, a week's worth of conversation history that generates maybe 50,000 text tokens it's stored normally.
Okay, 50K tokens, that's a lot to process.
Right. Processing that large text file every single time the agent needs to reference something from the past is computationally very expensive due to that quadratic cost. Now, what if we visually compress that entire 50,000 token history, maybe render it onto 5 separate high-resolution images, and then compress each of those images down to, say, 100 visual tokens using COC?
Okay, so 5 images times 100 tokens each.
You've reduced the sequence length required to represent that entire week of history from 50,000 text tokens down to just 500 visual tokens.
50,000 down to 500.
Wow.
That's a cost reduction factor of 100x, just in the attention mechanism calculation for retrieving that historical context.
Exactly. The agent saves massive amounts of time and money retrieving and processing its own long-term memory.
And the human memory analogy the authors drew in the paper is quite striking here, too.
Yeah, it perfectly captures the potential efficiency gain. Our own long-term memories, they aren't stored like high-resolution, perfect video files, right?
Definitely not. More like fuzzy snapshots or key points.
Exactly. They're often low-resolution, high-level summaries or these vague recollections. An AI agent could use COC to mimic this dynamic compression.
How would that work?
Very old, maybe low-priority context could be stored using the tiny mode. Just 64 tokens, very low effective resolution, highly compressed.
Yep.
If the agent then suddenly needs high detail on that specific old topic for some reason, it could retrieve that low-token compressed image, maybe decompress it back into a higher fidelity representation, or even reconstruct the text, and then run the full LLM reasoning over the detailed reconstructed information.
So this means the agent could dynamically resize its history's footprint. As a conversation ages and becomes less immediately relevant, the agent doesn't need to abstract away the details permanently via summarization.
Right.
It just needs to reduce the physical resolution, essentially, of the visual memory, maybe moving it from the Master mode down to the tiny mode over time.
Exactly. Thereby achieving massive compression without permanently deleting the fine-grained data, which might be needed later.
Wow. Okay.
It potentially transforms context management from a primarily destructive process, like summarization often is, into a highly efficient, adaptive archival process using visual compression. The potential cost savings and the capability to manage massive long-term context without major fidelity loss, that makes this arguably the most important implication of the entire paper. #tag outro.
Okay, so to bring this all together then, the DeepSeek OCR project seems to have successfully validated context optical compression COC as a genuinely viable and potentially highly efficient strategy to bypass that dreaded long sequence bottleneck in large language models.
Yeah, I think that they really proved the efficiency of essentially discarding the standard costly text tokenization paradigm, at least for certain types of input, in favor of this sophisticated controlled visual encoding method. Achieving things like 10.5x compression ratios while maintaining critical information precision is, well, it's impressive. And it was all made possible by that intelligent, somewhat minimalist sequential encoder structure they designed, which merges features effectively and controls the output token budget fiercely.
This research really strongly suggests that the input modality for LLMs might be fundamentally changing, doesn't it? Especially for dense long-form data. Why pay the quadratic cost of standard tokenization when a smart visual encoder can achieve such massive efficiency gains?
Exactly. And that leads directly to the final provocative thought that this work really encourages us to consider. If complex long-form text documents can be made so much more efficient by converting them into visual tokens first, what other forms of complex data could benefit from this same approach?
Like what?
Well, could complex scientific data sets, maybe raw audio waveforms, or even highly structured programming code? Could all of those be first transformed into some kind of efficient visual representation?
Interesting.
By leveraging the vision transformer's inherent efficiency at spatial compression, we might be unlocking a massive new avenue for efficiency and scalability across almost every aspect of large-scale artificial intelligence. It's a really intriguing possibility.
Definitely something for you to ponder until the next deep dive.
Absolutely. Thank you for joining us.